welcome to the n-Lorem podcast series, a series that focuses exclusively on patients now referred to as having nanorare mutations. I'm Stan Crook, and I'm the founder, chairman, and CEO of n-Lorem. n-Lorem is a nonprofit foundation that I initiated in January of 2020. Our mission at n-Lorem is to take advantage of the technology we created at Ionis Pharmaceuticals, Antisense technology, or ASO technology, to discover, develop, and provide experimental ASO treatments to nanorare patients, and to do that for free for life. And today we're going to be talking about a truly important and wonderfully fascinating organ, the liver. You can think of the liver as a combination metabolic factory and waste treatment plant. The liver is the largest organ in the body, and it's one of the few solid organs that constantly regenerates itself by producing new cells to replace older liver cells that die. Like other organs, the architecture of the liver reflects and supports its functions. And since the liver has both manufacturing responsibilities and waste treatment responsibilities, it must have access to lots of different blood from lots of different places. And so we'll talk about blood flow first. Oxygenated arterial blood is supplied by the hepatic arterial system, which of course branches off from the abdominal aorta, which is the main lower artery from the heart. This is the source of nutrients, building materials, and oxygen that the liver uses to do the work it does and to regenerate itself with billions of new cells every day. However, one of the other main functions of the liver is to sample blood from the GI tract and then use what it needs that is absorbed from the gut and clear any potential toxic substances that have been absorbed from the gut. It does that by having a special blood supply system that collects blood from the GI tract, and that system is called the hepatic portal system. The hepatic portal system is a set of veins that collect blood that contains what is absorbed along the entire GI tract and eventually delivers that blood to the liver. So every drop of blood that has had a chance to collect what is absorbed from the gut is filtered first by the liver before the rest of your body ever sees it. Being a part of the venous system, then, the pressure in the hepatic portal system, as you know, is going to be very low, and blood flow will be very slow, which is exactly what you need. The liver needs time to sample all those drops of blood and then waste treat them, or to absorb the good stuff. And it makes those decisions for you every minute of every day. To facilitate easy access to the hepatocytes, which are the cells in the liver that do all this work primarily, the blood vessels are quite porous, and they're called fenestrated. And that is, they have many tiny little pores. Fenestrae in Latin means windows. So the hepatic portal system has vessels that have many, many windows to open into the liver. Moreover, hepatocytes have specialized receptors called scavenger receptors that actively scavenge chemicals of all sorts from the blood, whether it comes from the liver or whether it comes from veins from other organs. Another source of venous blood to the liver is the blood that comes having passed through all the other organs. Remember that you deliver oxygenated blood with nutrients to all your other tissues through the arterial system, and then after those organs take all that they need in terms of oxygen and nutrients, they put all the waste that comes from the work that they do back into venous blood, and that venous blood then, where does it go? It goes to the liver. So it's important to understand that the liver has these blood supply processes to assure that you're protected from toxins absorbed from the gut, as well as toxins that you might produce in terms of the waste that all your cells produce as they do their work. So, key point number one, the liver samples every single drop of blood from the gut via the hepatic portal system. It also samples every single drop of venous blood from the system that collects venous blood from all your other organs. Finally, it also gets nutrients and oxygens like every other organ through the arterial system, the hepatic arterial system. I forgot to mention that the main vein that collects all the blood from other tissues is called the inferior vena cava, meaning it's below the liver, and vena cava meaning the biggest vein in your abdomen. So you have a hepatic portal vein, which comes from the gut, and the inferior vena cava that brings all the blood from the rest of your bodies to the liver. Make sense? Now, the liver's set to do its waste management. What about the architecture of the liver itself? Well, it's composed of 5 identically organized lobes. And to do their job, hepatocytes, that is the liver cells that do the work, must be near oxygenated blood to acquire nutrients and all the oxygen and whatnot that they need, but they also have to be close to the hepatic portal system and the venous blood that's collected into the vena cava to do their job as waste management. They have a special sort of system. Within each one of these lobes, there are these tiny, tiny little lobules, microscopic size, in which liver cells are arrayed around an arterial blood vessel, a venous blood vessel, and then the bile duct. The bile duct opportunities are ductules in the case of the little lobules. Their job is to be the sewer, if you like. So when the liver is busy getting rid of all the junk that you really don't want, and it certainly would make you sick, often, most of the time, it secretes that into bile. And bile collects in the gallbladder. And that's why your aunt or your uncle or your mother or your father had gallbladder surgery when they were 52. And why you'll have gallbladder surgery someday probably as well, because it stores all the junk, all the garbage, all the toxic stuff that you have. After being stored in the gallbladder, the bile then is delivered to the gut. And it's delivered to the gut in a place where it can end up in feces. So it's a complicated system, but if you think about it simply, the liver's got to have oxygen, it's got to have nutrients because it's got a lot of work to do, but it also has to have all the different bad blood so it can sample that, get rid of it, and it needs to have a sewer, and the sewer is your bile duct system. So now moving on, one of the major things that the liver does is metabolize. So a primary job of the liver then is to process nutrients and toxins that have been absorbed from the hepatic portal vein and degrade them into their essential building blocks. Many of these things are larger molecules comprised of units. Remember we talked about polymers? Polymers are big information-containing molecules that have a lot of different units, and so those things have to be broken down. Some of the basic nutrients include sugars, carbohydrates, fat or lipids, proteins, other types of chemicals, and even nucleic acids. Long before the liver is exposed to these chemicals, if you ate them, enzymes in the gut provided by the pancreas and the bacteria in the gut and the cells that line the gut process these chemicals many times into their building blocks so that the liver already gets them pre-processed. And remember that the bacteria in your gut is called the gut microbiome. You hear a lot about that these days. You want to take your natural supplements so your gut microbiome stays healthy and yada, yada, yada. Some of that's true. Most of it's probably hokum. Now we talk about carbohydrates. Carbohydrates, like starch, are broken down into smaller sugars, such as sucrose, such as stuff you put in your coffee. Fats are degraded to smaller lipids. And proteins are degraded to smaller peptides and amino acids. Really simple. These are big polymers made up of repeating units. You break them down to the units. Pretty simple. Other chemicals and toxins may be partially metabolized, or they can enter the liver intact. Complex sugars and polysaccharides then are degraded by enzymes secreted by the pancreas, and they're called amylase and maltase. They're degraded into those simple sugars, and those are called monosaccharides. Mono, one saccharide sugar molecule. One sugar molecule. Polysaccharides, many. Big words when simple, smaller words would do. Long before you get to the liver, if you're eating stuff, lots of metabolism goes on Otherwise, you wouldn't absorb the stuff you need to keep living. And the liver then is the beneficiary of that because it gets a lot of pre-processed materials. Make sense? Again, it's like a giant waste management system. You want to take what is in this gunk that comes from your gut and extract what you want to use and degrade the stuff that you don't. And in the process of doing that, you have to take these complex biological molecules and break them down, whether it's something you want to use or whether it's something you want to get rid of. Then the next step is work that the liver cells, the hepatocytes, have to do. And the hepatocytes are an amazing bunch of cells. They're equipped with many, many thousands of enzymes that are organized into different pathways to take different types of chemicals and degrade them in the way that the liver wants to do to keep you healthy. So enzymes, remember, are just proteins that facilitate chemical reactions. Since you eat a lot of protein, there are a lot of proteases, and they degrade proteins to amino acids. And since you eat a lot of sugar of various kinds, you have polysaccharidases that degrade these big polysaccharides into smaller. And what do you degrade them to? Things like sucrose, fructose, and things like that, glucose. When you drink a soda, you're getting a lot of fructose, and it turns out fructose is managed by the liver very differently from sucrose. The whole point of all this is you're degrading the proteins to amino acids so you can reuse those amino acids or use them. You're degrading the big complex sugars into the small units so you can make energy with them and store it. And then fats are degraded by what's called oxidation. And oxidation doesn't mean anything other than you're using oxygen to do some work. The first step in that process is to convert them from a fat to an acid, making them more acidic, making them more water soluble. So the way that's done is your fat comes in a long, skinny chain. Think it would be fat, but it's actually a skinny chain. And so those things are degraded from one end of that fat, sort of 2 units at a time. And that's called beta elimination. Once again, to just recapitulate, the simplest way to think about metabolism is that chemicals are broken down constantly to their building blocks to be reused or gotten rid of. They can be oxidized, meaning we use oxygen to make them more positively charged, or they can be reduced to make them neutral or less positively charged. Often, the liver adds other things to these metabolites to help do things, sometimes to make them more soluble in water. So you don't have to put them in bile, you can put them back into blood, and then you can urinate them. One of the most common things that is coupled to a metabolite or to a chemical is glucuronic acid. That's called conjugation. When you conjugate glucuronic acid to another molecule, all you've really done is you've made it more water soluble. So you'll find it in your urine instead of in the bile, or sometimes both. You're made of water. So naturally, anything that isn't water soluble, you really want to convert to water soluble molecule, right? I mean, if you were made of 100% fat, you'd do it the other way. But you're, 98% water. So metabolism, breaking things down and using them or getting rid of them, and you oxidize, reduce, and then you conjugate. But that does something to make that chemical more useful. It's really that simple. What about xenobiotics? Well, xenobiotics means foreign. That's all it means. So xeno, foreign, biotic, a foreign biological material. So we're constantly exposed to xenobiotics. We breathe them, we eat them, we absorb them from our skin, we do all kinds of things with these non-us chemicals. And these include natural chemicals in food, so-called natural products, including vitamins, minerals, and the ever-growing list of supplements, as well as, of course, recreational drugs, including alcohol and other drugs, as well as medications. Medications that are legal, either over-the-counter that you can buy yourself or you have to have a prescription. All of those things are xenobiotics. And remember, I told you that the only difference between a drug that you take therapeutically and any other chemical is intent. The drug doesn't care, it just goes in your body and does what it does. But somebody has selected that as something that's good for you. if you have a problem. Like if you have an antibiotic, you're obviously infected, you're taking the antibiotic because you like to get better. Every xenobiotic, every foreign chemical that you take into your body can be toxic, even water. And almost all of these chemicals, the effects that they have are dose dependent. The more you take, the more the effect. And so you're constantly interested in dose. What is the dose of this stuff I'm eating? What is the dose of the drug I'm taking? What is the dose of the alcohol I'm ingesting? The more you take, the bigger the effect. And if you're thinking about side effects, adverse effects, you know very well the more you take, the worse the worse you can get. The more alcohol you drink, the worse the hangover. In simple terms then, any chemical that's foreign to your body that you take can potentially do you harm. And that's true whether it's called natural or not. The notion that natural products are safer is insane. All of the original poisons came from natural products. Curare is a very natural thing, but it ain't good for you. Strychnine is a natural product, and so on and so on. Where do all these xenobiotics go? Well, you already know. As soon as you ingest them, they go straight to the liver, and the liver's trying to do its job to keep you from killing yourself by all the garbage that you put into yourself. You really love your liver now, though, even more than you once did, right? Okay, so one of the most important functions of the liver is to metabolize waste products that other organs produce and the xenobiotics, non-U compounds that come from the gut. Its job then is to just break those down into component parts and then make them usable or make them more easy for you to get rid of. Another key point, the liver sits at the nexus of blood coming from the gut, venous blood coming from other organs, all around the body. Plus, of course, it has its own arterial blood supply, and it has a sewer system. So it has all the things it needs to do its job as a waste management system. The liver is busy 100% every second of every day protecting you from the things that you do to yourself. Many of these things are very, very toxic to liver cells. And as a consequence, they die. And that's why you regenerate billions and billions of liver cells every minute of every day. Pretty neat, isn't it? You let this organ take a hit for you constantly, but you make sure that it survives because you make a ton more cells to get, replace the cells that you just killed. Kind of a remarkable solution to a set of behavioral issues. The other thing that liver does is it's a factory, and it has an amazing array of products that it makes. If you think about the factories that you're used to thinking about, they make a component for an auto, or they make a thing for your computer, or they do this. Liver is like having the entire GNP of the U.S. making everything that is in the U.S. that we use. Kind of amazing, don't you think? So what does it make? Well, it makes fat. You need fat, a certain amount. So the liver takes single carbons. Remember, carbon is the building block of life. It takes these single carbons and forms long chains of carbons in a row. And since a long chain of carbons in a row is very water insoluble, it's called fat. If enough of it accumulates, it forms gooey gunk that looks yucky. It's also called fat, but it's just a chemical. One of the lipids, for example, that is made in the liver is cholesterol. And there are many types of cholesterol, actually. Many lipids made by the liver are chemically bound to proteins that are called lipoproteins. Lipo, meaning lipid, so these are proteins that have a big hunk of fat stuck to them. Lipoproteins. And you hear about lipoproteins all the time because you're worried about your cardiovascular health. These lipoproteins play many important roles in health and disease, and there are good lipoproteins, and you hear about that. That's my good cholesterol, HDL. And then there are a slew of bad lipoproteins. LDL cholesterol, VLDL cholesterol, ApoB100, ApoA. Lipoproteins can be good for you, can be bad for you. All of them function. It's only a question of how much of each you have. All of them have some function or they wouldn't be made, but lipoprotein then just means a protein that has attached to it fat. Triglycerides are another fat that's made in the liver, and they're generally not covalently bound to proteins, but they often, they're free in your blood, but they will also sit down on proteins for a while and take a break, but they're also made in the liver. The liver is a factory. One of its products is lipids and fatty acids. Many of those lipids and fatty acids are packaged not as free lipids or fatty acids, but as protein complexed with fat or fatty acids, and those are called lipoproteins. As you well know, those lipoproteins can have a profound effect on other organs. So here you have the first example of the liver making something that not only can have an effect on the liver, but can affect many other organs in the body. That's a central theme. The liver is a factory. The liver makes things that can be good for the liver, bad for the liver. It also makes things that can be good or bad or both. Most of these things are both for all the other organs in the body. What else does the liver make? Well, it makes proteins. Now, the liver synthesizes many proteins with specific functions. For example, as mentioned before, it is responsible for synthesizing the proteins that carry lipids that form LDL and HDL and all that other stuff. Who makes the proteins that comprise your lipoproteins? The liver. The liver makes a variety of protein hormones like erythropoietin and thrombopoietin. And those two, as you know, stimulate bone marrow to make either more red blood cells or platelets. And if you're Lance Armstrong, it gets you multiple Tour de France championships until they take it away from you. The liver also makes an array of proteins that carry important chemicals, like vitamin A. And you need that because vitamin A is a big fat, and the protein carries it, and the proteins carry it to where you want your vitamin A to go. These proteins that are carrier proteins do a lot of hard work for you. But like any other protein, they have a structure. They're folded in a certain way. Sometimes these proteins misfold. Either you have a mutation or who knows why. When they misfold, they're no longer soluble in blood at the same way, and so they precipitate out. And that's called amyloid. You've heard a lot about amyloid in the brain. That just means pink stuff that you can see on a microscope stain that shouldn't be there. It's a bunch of proteins that have aggregated. But amyloid can form in other organs, such as the kidney or the heart and muscle. And anytime you form an amyloid deposit in any organ, you're going to do real harm to it. And so now there are numerous new medications that, in fact, Ionis and others were involved in that get rid of amyloid proteins and kidneys and livers and muscles better. Another vital set of proteins are clotting factors. You know that you have 12 clotting factors. They're all made in the liver, and they're all very similar. They're all proteins, and they're all proteins that would degrade other proteins, except they have a flap, an extra piece of that protein that keeps it inactive. And then cascade is another protease that comes, removes the flap, and then that protein can go to work to take care of what you need to do when you clot. So why would you do that? If you cut your artery or you cut your vein, you're going to want something that can go to work immediately. You don't want to wait 5 minutes to make it. So it's floating around the blood, and it's there as soon as you need it. But you don't want it to be clotting your blood if you don't need it, because that produces things like heart attacks and strokes and lots of misery. This ingenious solution of making what's called a preprotein or proprotein that can be cleaved as a part of a cascade that's activated when you need it. That's a common theme. Isn't it beautiful? I mean, it's just amazing how you work. These clotting factors are inactive. They float around the blood constantly, protecting, checking to see if you got any leaks anywhere. If you have a leak, they spring into action, and in this cascade, you are protected because the cascade only happens in the right way if it's stimulated by need. You need to stop bleeding. There are also proteins that are made that control your blood pressure, like angiotensinogen. There are drugs that are called angiotensinogen inhibitors. That's what they do. There are many other classes of proteins that respond when you're infected, and you need to respond to protect yourself. All of these proteins are made by the liver, and they circulate in blood constantly looking for problems that might cause you real trouble and responding in various ways. Some other proteins are made in other cells, like inflammatory cells, to contribute to what the liver does. The final class of proteins gets a little complex, and they're called complement factors. When the chips are really down and you need acute phase reactants, including complements, these things are really dangerous. But when the chips are down and you've got a bunch of bacteria that are trying to kill you, all of these systems conspire to work together to bring you into alignment and get rid of all these things. Think of it as a tiered system to assure that your blood is flowing properly, that when you need to bleed, you bleed. When you need to clot, you clot. When you need to respond to an infection, you can. When you need your blood pressure up or down, you can do that. And if there's a real emergency, you can respond with the army that you have at your disposal to protect you. All that's happening in blood, and all of it is produced primarily by the liver. Liver's pretty important, don't you think? The list of proteins that are produced and secreted by the liver is enormous. I couldn't begin to tell you all the proteins that are made that way and secreted. You might ask, well, if the liver makes all kinds of proteins, some of which it uses itself and some of which it exports, how does it know which ones are going to be exported and sent out to the periphery and which ones it keeps? It's a factory. So which ones does it keep, which ones does it ship, and where does it ship them? Well, as you can imagine, there's a special system to decide to help you secrete the proteins that you're supposed to secrete. And again, I think that's wonderful. The system gets very complicated, but basically, while proteins are being translated, they are marked, typically by carbohydrates. And if they are marked, it's like putting a stamp on a letter. And once that stamp's on the letter goes into the mail slot, and there's a process that delivers it then in a way that it can be secreted into blood. There is this system designed to put a stamp on proteins that need to be shipped. It's pretty cool. And you've heard of some of these things. You've heard of the Golgi apparatus and the endoplasmic reticulum. And what you really need to know is that the liver makes two kinds of proteins, basically. One set that it keeps for itself, and another enormous set that get exported. Those are the products it makes for the other organs. And to make sure that those proteins get out where they need to go, they get stamped during production with an order to deliver them where they belong. Pretty simple. As a key point, the liver makes many proteins. Some it keeps for itself, and then hundreds and hundreds it exports to help other organs perform their jobs. Many of these proteins that are exported control lipid levels, others are clotting factors, others are help you fight infections, others respond if you are in really deep trouble. All of that is coordinated in blood with proteins made by the liver. Finally, the blood makes proteins that tell other organs to make some more cells, like erythropoietin and thrombopoietin and all the other poietins that you hear about if you have anemia or you have some other kind of problem. Wonderful, complex factory that does so much for you. It's hard to imagine what life would be like without a liver.
n-Lorem is a nonprofit committed to discovering and providing personalized experimental treatments for free for life to patients with genetic diseases that affect 1 to 30 patients worldwide, referred to by n-Lorem as nano-rare. Many of these patients progress and die without ever achieving a diagnosis. This is where n-Lorem comes in. They do the impossible by providing hope, and for those that they can help, free lifetime treatment. For more information about n-Lorem or today's episode, visit n-Lorem.org. Any questions can be sent into podcast@n-Lorem.org. Search n-Lorem on Twitter, Instagram, YouTube, LinkedIn, and Facebook to connect with us. Please rate and review the podcast on Apple, Spotify, or wherever you listen. This truly helps us climb the charts and allows others to find the show. This podcast is hosted by Dr. Stan Crook. Our videographer is John Magnuson of Mighty One Productions. Our producers are John Magnuson and Kira Deneen of DNA Today. Thank you for listening.